if there is a coexistence equilibrium, then there'll be a point in the positive quadrant where they intersect. And there could be more than one. But typically, in most of the models, there's only one. And we can, for example, decide whether that equilibrium is what kind of equilibrium it is. And how do we decide what kind of equilibrium it is? So firstly, we've got to solve for the equilibrium. Then we've got to generate what's called the Jacobian matrix. The Jacobian matrix, and this is what we talked about last time on Tuesday, is the partial derivatives of the first function with respect to x1 gives you your first term. The first function with respect to x2 gives you your second term. So that's the top row, first column, second column. And then the partial derivative of f2 with respect to x1 gives you the second row, first column. And f2 with respect to x2 gives you the second row, second column. You take these derivatives and you evaluate it at this equilibrium, and you get a bunch of numbers. You look to calculate the eigenvalues of this matrix. A 2x2 matrix, can have either both eigenvalues are real and positive, in which case the equilibrium will then be an unstable node. Both values could be negative and real, in which case it's a stable node. One of the eigenvalues could be real and positive, one real and negative, in which case it's a saddle point. Or you can get this case where the eigenvalues are complex conjugate pairs, in which case you've got a spiral. If the real part of the complex conjugate pair, of these complex conjugate pairs, if the real part is negative, the spiral is stable. If the real part is positive, the spiral is unstable. So when you take the Jacobian and you solve the eigenvalue equation, you get an equation for the eigenvalue that looks like this in lambda. This is lambda, and this is the trace of the matrix, and this is the determinant of the matrix. And if you solve this equation and you use your formula, your quadratic formula, your first eigenvalue is going to be equal to t. Remember that the coefficient in front of lambda is a 1. So, it's going to be t upon 2. Everything's divided by 2 here. But it's going to be t plus the square root of t squared minus 4d upon 2, or it's going to be t minus the square root of t squared minus 4d upon 2. This is going to be an imaginary number. You'll get an imaginary number by taking the square root of a negative number here. If you get an imaginary number if this is negative, and these will both be real if this is positive, and these will be conjugate complex if this is negative. If I plot out the value of t and the value of d in TD space, so here's TD space, t and d are variables. I'm looking at the value of the trace of the matrix, I'm looking at the value of the determinant of the matrix. In TD space, the equation t squared minus 4d equals 0 is a quadratic in TD space. So it's this line, it looks like this quadratic equation. Above this quadratic equation, t squared is smaller than 4d, and below this quadratic equation, t squared is greater than 4d. On this side of the d-axis, to the right, the right-hand side of this plane, t is positive, and on the left-hand side, t is negative. So if t is positive or t is negative, and this is imaginary, this is going to lead to the case of if t is positive, you'll have unstable spirals. If t is negative, you'll have stable spirals. Yeah? This is a plus sign here, and this is a minus sign. So remember, in this formula, in the quadratic formula, it's always a term over here, plus or minus this discriminant. That's how the two roots. So this is just your basic algebra of quadratic equations. So from your algebra of quadratic equations, you can work out if both roots... so what you can work out is that above this line, that is d positive, then you get the situation where if t squared is greater than 4d, so that you're below this line, but still d is positive, then what will happen is one of these roots will be positive and one will be negative. And so you'll get, both roots will either be positive or both roots will be either be negative. If both roots are positive, it's a stable node. If both roots are negative, both roots are positive, it's an unstable node. If both roots are negative, it's a stable node. And if d is negative, then one of these lambdas will be positive and one will be negative. Because here you've got t, and you're adding something that's positive, so that's going to be the positive one. And here you've got t, and you're subtracting something that is the size of t squared, the square root of t squared, if d is 0. But if d is negative, then you're subtracting something on this side that's bigger than t. And so lambda 2 will turn out to be negative. You can work through that algebra and you can see this. So this is what I require you to know this stuff in here. I require you to know the following. If you've got a nonlinear system in 2 dimensions, and you solve for an equilibrium, and you want to know whether the equilibrium, what its stability properties are, then you generate the Jacobian matrix, evaluated at equilibrium, and you find its eigenvalues. And the eigenvalues will be one of these cases. And depending which case it is, you'll be able to say if the equilibrium is positive, the equilibrium is a node, a stable node, or an unstable node. The only case that I haven't dealt with is what happens when, for example, this is pure imaginary. In other words, t is 0. What happens when t is 0? So that means you're on this line. When t is 0, you're on this vertical line over here. When t is 0, if you're on this vertical line, then you're halfway, then you're kind of in the middle of being stable and unstable. And we call that a neutral center. So I haven't put an emphasis on these in-between cases. What happens when you're on the line over here? Are you a node or are you a spiral? Well, in fact, you're in transition from being a node to being a spiral. So when you lie on these different curves, then the case is not resolved on what you are. But when you're in these spaces, when you're in these different parts of the plane, in TD space, then it's clear what you are. So there's certain degenerate situations where you happen to actually be right on the curve or right on this line, and then you're halfway between two cases. And you don't have to worry about that. I mean, the chances of that happening are very, very small, and they only happen in very peculiar cases. For example, the Lotka-Volterra prey-predator in the simplest model is one of those peculiar cases where you've just taken the basic exponential growth of the prey, exponential decline of the predator, and this mass action term for extraction is proportional to xy. And when you do that, it just so happens that the trace will turn out to be 0. And so you'll be on, and so the case you'll get will be a neutral center. Okay, that's all I want to say about the midterm, about the final. Are there any questions about the final that you might have? Remember, bring your 2 blue books or your 2 green books. If you don't have those books here, then it creates a big problem for us. Because, I mean, the risk you take is that if you write out stuff on sheets of paper, that a sheet of paper can get lost, and then it's unaccounted, and then it's lost, and you lose, and we can't recover anything. Yeah. 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 I mean, I'm pretty much in the whole week, and so you can just email me at your convenience, and I'll meet with you. Yeah. Anything else? Okay, so we have course evaluations for you to fill out. I guess you know how it works. I'll hand these out, and then you fill them out. I'll leave the room, and somebody has to volunteer to kind of gather these together and take it to room 145. So you'll volunteer. Okay, thanks very much. And then, yeah, so I don't know if you both want to do both, or if you primarily interacted with one GSI and not the other, then I guess, your name's on, yeah, okay. Okay, and as I said, these do form part of professors' evaluation packages, so it's your opportunity to make a statement, and it does play a role in the university system. And when professors come up for merits and all sorts of things like that, then there are 3 components to what we do. One is our research record, the other is our teaching record, and the third part is our service record. So this is weighted towards the teaching record, and unless you're a Nobel Prize winner, in which case you can probably blow off teaching, you tend to get into trouble if you're not getting good ratings in your courses. So it does really count. And so you should take it seriously. So when you fill it in, please think about the questions and put down what best kind of fits your view of the course. Also remember, fill in the dot, like a little round dot. Can everybody see that? Don't put a cross through it. So none of these signs are appropriate. The only one that's appropriate is to make it a little black, to just color the dots in so that you have black circles on the page, because these are obviously read by machines. Okay, so I'll go ahead and hand these out. And I think, why don't they finish this first, and then otherwise these things will get a bit mixed up. So can you pass those around? Let's see, pass those around. I think we need to pass a couple down there. How are we doing? Let's see. Oh, okay. Right. And so has everybody got one of these? Anybody need one for my part? Okay, thanks. So fill those in and then put them in here. And then once you've done that, then you can pick those up. And then do they all go to 145? Yeah. Okay, so I hope you got a lot out of this class. And good luck for the finals. Good luck. Have a happy holiday season. And good luck for your futures. And remember, the world's not going to change if you're not going to change it. It's not hard, it's the truth. So we live, unfortunately, in troubled times still. One would have thought that we would have solved all problems associated with race, but we don't seem to have done that. Also, it would have been nice if all politicians believed science and the existence of global warming, but even that's not universally accepted.